I'm going to go ahead and start, and then I'll let people in as they join. So I'm going to start the chapter on organic chemistry. And I'm going to kind of pick and choose what I spend time on because I think I'm going to cover sections 1 and 2 today because I think there's a little bit of information in section 1 that's relevant, and section 2 starts to get into more of the details. So I'll be covering those 2 sections. All right, so the first section is basically just about carbon in general and how carbon bonds. And some of this should be a review anyway, from grade 10 when we talked about bonding and specifically about, what do you call it, hybridization. Although I'm not sure if, oops, I guess that exits, if you guys will remember or not. So like I said, that can be kind of a review. Where is my mouse? Oh my gosh. Okay. All right. So the important thing about carbon is not necessarily that it's non-metal, but its ground state electron configuration. If you remember what ground state configuration is the lowest energy level of the atom. So in its ground state, the electron configuration is 1s2, 2s2, 2p2. And do I have, hold on a second. I know I have a periodic table. Where is it? Let me, there's somewhere. There we go. All right, so I got to do a new share. There we go. Okay, so carbon is here. And so we basically have 1s2 being hydrogen and helium. We've got 2s2, which gets us to beryllium, and then 2p2 because there's 2 electrons here. Just to kind of review that. Which one is it here? So that is the first part, what is what leads us into the problem with carbon bonding, because if I were to draw out orbital notation, which is like this, we get 1s and then 2s, there's 2 electrons, there's 3 orbitals in 2p, and then there's 2 electrons there. Now, the biggest problem with carbon bonding just from this point is that the valence electrons are the 2 in 2s and the 2 in 2p, because remember, valence electrons are in the highest energy level, and both 2s and 2p are in level 2. So all 4 of these electrons are valence electrons that are available for bonding. However, there's 2 problems. First problem is these 2 electrons are already paired up. And the second problem is that you've got 2 lone electrons in this third p orbital that has no electrons in it. And the other problem is the fact that 2s electrons are slightly lower in energy than the 2p electrons. If you remember back to Aufbau's principle, I'm not even going to get out the diagram, but it was a diagram in your book that talked about the energy levels of the orbitals. And so the reason why you fill 2s first before 2p is because you have to fill in the lowest energy level, or the lowest energy level orbital that can hold an electron. So that means that the 2 electrons here in 2s, like I said, are slightly lower in energy than the 2 electrons in 2p. So why is that a problem? Because if carbon is going to form 4 covalent bonds with 4 different atoms, those 4 electrons have to be equal in energy. And the way that this configuration is, the 4 electrons just aren't in the same, they don't have the same energy. Okay, so I mentioned 2s and 2p. All right, so what happens is something called hybridization. And that's what you're seeing down here, hybridization. And hopefully we know what hybrid means. It's like to mix two different things. So if we've got 2 electrons here, this indicates energy level. The 2 electrons in 2s and the 2 electrons in 2p, the 2s orbital and the 2p orbital are going to combine together to form 4 individual orbitals that are all at the same energy level, somewhere in between 2s and 2p, which you can see based on its vertical position. So that's why they put the arrow here. It's between the 2 original orbitals, but you've got, this is called an sp3. I did cover that in grade 10, but again, I'm not sure if you remember it. So I just wanted to mention it again. So now you've got 4 valence electrons that each have the same energy. And now it can form 4 single bonds that all have the same energy. And the reason why it's called an sp3 orbital hybrid is because you're taking one s orbital and you're taking all 3 p orbitals. You do have hybrids. You've got an sp hybrid and an sp2 hybrid, and that just depends on how many of the p orbitals you're actually including. So for an sp orbital, you're just going to have 2, and for an sp2, you'll have 3. So one of these will be an s, and the other 2 will be p. And here's 1 s and 1 p. And what determines what kind of hybrid you form is basically just how many valence electrons you have. So if you look at something like a covalent bond with lithium or beryllium or boron, that's when you're talking about combining orbitals that give you either sp or sp2. Okay, so this explains the geometry. Because we have sp3 orbitals, we've got 4 orbitals of equal energy. And we know that if we have a centralized atom here in the middle with 4 bonds, it's going to go to the greatest distance away from the other bonds possible, and that's going to form tetrahedral. The text is kind of cut off there, but tetrahedral geometry. Now, carbon atoms can form double bonds through sp2 hybridization. When a carbon atom forms double bonds, the sp2 hybrid orbitals of both carbon atoms lie in the same plane. And that is the difference between a sigma bond and a pi bond. Again, I think we talked about that in grade 10. So if you've got an overlap of 2 sp2 orbitals that lie in the same plane, that's sigma. But if you have an overlap of a p orbital and an s orbital, that's a pi bond. In ethene, which is C2H4, all 6 atoms lie in the same plane. So here's an example of a sp hybrid orbital. This is what you have when you've got a triple bond. And you can see here, you've got the pi bonds are the ones that stick out, that don't lie in the same plane. And the sigma bonds are the ones that lie in the same planes, basically in a straight line. So this is ethine, which is C2H2. That's the triple bond between carbons. 1 second, I gotta let my dog in. Sorry, otherwise he will just sit and whine and scratch the door. Okay, and then the last topic for section 1 are allotropes. Now, you already know what allotropes are. You might just not know what the name is. It's basically pure carbon, but in different forms. So you've got pure carbon. I'm sure you could probably think of 2 examples of what do you call that? Like pure carbon substances that are completely different. These are allotropes. So two or more different physical forms in which an element can exist. The two commonly thought of allotropes for carbon are diamond and graphite. For diamond, of course, we know is a colorless crystalline solid form of carbon. Graphite is a soft black crystalline form of carbon that is a fair conductor of electricity. But one you might not have heard of is a fullerene. Excuse me. This is a spherical network of carbon atom, and it kind of looks like a cage. Now, I don't want to get into like super detail about the properties and differences between these, because I think most of them are pretty obvious about diamond and graphite. But just to kind of go through it, diamond is the hardest material known. The reason for that is because here you can see the carbon atoms. They form this very highly bonded network. So each of the green dots that you see in the diagram is a carbon atom. So each carbon atom is tetrahedrally oriented to its four nearest neighbors, and that, what do you call that? That contributes to its strength. Right, so we know that either they are precious gems to be used in jewelry, but they also, because they're so hard, they are used in drilling bits and what do you call that? Like saw blades. You got like diamond crusted saw blades, but of course they're not going to be gem quality diamonds. It's going to be kind of like diamond dust kind of thing. Okay, is more conductive to heat, but of course it's going to be super expensive, so we're not going to use that for conduction. Then we have graphite, and graphite is almost known for its softness in the same way that diamond is known for its hardness. And so it crumbles easily. And the big difference here, this is what I wanted to focus on. You see the structure of diamond on the left-hand side and graphite on the right. Now, graphite forms carbon networks that come in layers. And so that's why it's very brittle and it's easy to snap off, because it can just snap off in layers. Kind of the same way that I talked about again in grade 10, and I don't know why so many topics in grade 12 go back to grade 10. The only thing I can think of is that grade 10 is where you form like the foundation of everything that you learn in chemistry. So it often goes back to foundational knowledge. But when I talked about the difference between the hardness of ionic compounds versus covalent, and ionic compounds being that if you have something made up of charges like this in alternate layers, if any of these layers shift, then you're going to have repulsive forces between the shifted layers. So let's say this layer 3 is shifted to the left by 1 unit. So this positive comes out here, this is negative, this is positive, that's negative, like that. You now have repulsion between these two layers, and so it'll split in between the two. So a similar kind of thing happens with graphite, only it has nothing to do with charge. It just has to do with the fact that the networks are formed in layers, whereas diamond is a complete network. Okay, that doesn't really matter. Who cares? Let's get to the fullerenes. Okay, so fullerenes is the one that maybe you've not heard of before. It was discovered in the mid 80s. And in 1996, these guys, or yeah, they're all men, earned a Nobel Prize in chemistry for it. There is a fullerene. Fullerenes are part of soot that forms when carbon-containing materials are burned with limited oxygen. So a lot of times when you see like those big trucks that are driving down the road and they spew out that thick black smoke, fullerenes are going to be part of that. So you see it's a nearly spherical cage of carbon atoms. The most stable fullerene is C60. This is 60 carbon atoms arranged in an interconnected 5 and 6 member rings. And sometimes they call this the buckyball. So it's resemblance to geodesic domes. One of the guys named it Buckminster Fullerene in honor of this architect named Buckminster Fuller. So a lot of times you call that cage buckyball. Yeah, here we go, buckyball. And obviously we don't really have any practical uses for it. Okay, so that's section 1. Like I said, it's pretty short and not terribly interesting, but when you get into section 2 and actually talking about how carbon forms forms compounds, organic compounds, you get more to the meat. But I'm not actually going to get into hydrocarbons today because I want to talk about isomers mostly and explaining how those work. So we hopefully remember that all organic compounds contain carbon, but not all carbon compounds are organic. Specifically, the 2 groups that are omitted are the oxides and carbonates. So any carbon oxides would be like carbon monoxide, carbon dioxide. Even though they contain carbon, they are inorganic. And anything that contains carbonate, and if you don't remember carbonate, it is CO3 minus 2. These compounds are not organic. Okay, I just mentioned that. So excluding carbonates and oxides, they are covalently bonded carbon compounds. Those are organic. Now, the amount of organic compounds, which you will find out more than you ever wanted to know in this unit, the variety of organic compounds is huge. And probably you won't remember all the way back to like the very beginning of bio when I talked about carbohydrates, proteins, lipids, nucleic acids. One of the first things that I mentioned was carbon bonding, the fact that carbon can have single, double, or triple bonds. So I don't know what you call this, factorizing or something in math, all the possible combinations. So carbon can form single, double, and triple bonds. It can also form straight chains. It can form branched chains, and it can form rings. And you have all any combination of any of those things. So whatever you call that, all that forms a huge variety of compounds. Not to mention the fact that like in the later part of this unit, we'll start adding functional groups. So when we start talking about alcohols, amines, ethers, esters, carboxylic acids, et cetera, but we start with the basics first. So the type of bonding that makes carbon special is called catenation. Again, with the phonetics explaining how to pronounce it. And catenation just means that an element or an atom can bond to itself. Not a lot of elements have that ability. Carbon has a huge ability to form thousands of different types of molecules by bonding to itself. Okay, and again, chain, a straight chain, branched chain, rings. You also have single, double, and triple bonds. Carbon atoms can also bind easily to elements with similar electronegativity. Of course, that will be anything that's kind of around it on the periodic table. One of the atoms that carbon loves to bond to is hydrogen. This is why tomorrow I'll be talking about hydrocarbons. These are the simplest organic compounds. They contain only carbon and hydrogen. And there's going to be 3 classes that I'll talk about tomorrow based on whether they contain single, double, or triple bonds. All of the other organic compounds you're going to learn about are going to have hydrocarbon backbones, and they're going to have other elements or other functional groups attached. And they're going to be classified according to their functional group. Okay. Right. So then we get into isomers. I have mentioned isomers in the past. Again, probably grade 10. Talking about glucose, fructose, and galactose, all having the formula of C6H12O6. but having different structural formulas. So one of the most important things that you're going to be doing in this entire unit is we're going to get rid of chemical formulas and we're going to start drawing structural formulas. That's why I showed you, I shared that meme about what people learn in organic chemistry is basically how to draw the perfect hexagon, which is kind of true. So isomers, just to remind you, are compounds that have the same molecular formula or chemical formula, but they have different structures. Now, you don't have isomers in organic compounds until you have 4 carbon atoms. So for any hydrocarbon that has 3 or less carbon atoms, they do not have isomers. I should say they don't have structural, sorry, they don't have structural isomers. They might have geometric isomers, but I'll talk about that in a minute. For example, if you have a C8H18 that has 18 isomers, if you increase that by just 1 carbon and 2 hydrogens, you nearly double the amount of isomers, right? So you just compare the formula. We've only added a CH2 unit, which is very common in organic chemistry, and we've doubled the amount of isomers that are possible. If we do it again, we add another CH2 unit. So we're only really increasing the size of the molecule by 1 carbon. You, again, more than double the number of isomers. For C40H82, I don't even know, is that trillion? Is that 1,000, million, billion, trillion? Yes, like almost 70 trillion possible isomers. I'm not going to ask you to sit down and write out all of the isomers for these kinds of things because, well, I think it's just kind of a waste of time. I might do it maybe as an assignment or something, or occasionally, because it's just good practice to kind of figure it out. But as a regular thing, no. So I mentioned that we're going to be focusing on writing structural formulas. I will have you write condensed structural formulas I'll have you drawing condensed structural formulas as much as possible. But for now, we'll just do the whole, uncondensed version. So what you see in the bottom right-hand corner is an uncondensed, completely expanded version of a structural formula. And the reason why this is different is that it shows you position of atoms as well as the number and types of atoms. So one of the ways that I could condense this down. Oh yeah, so that's okay. So the first thing that we can do is we do not show the single bonds between hydrogen and carbon. We literally just write the symbols next to each other, and it's understood that it's bonded to the element that's next to it. So for example, on the previous slide, what do we have? Something like this. And then there was hydrogen here, something like this anyway. I hate drawing it like this. It takes so long. Okay, so the first thing that we can do to condense this is to get rid of all of this. And we just say CH3. And then the middle, that would be CH. And then this is CH3. So we treat them as chunks, I guess. Okay, so that's one way to do it. And the way that I prefer to do it is, I don't even know what you call it, like super condensed, I'm not really sure. But the way that I would draw this is basically like this. Let me make that better. Okay, so this is the method that I prefer. I will be using this method for now until we get used to it, but this is the one that you guys are going to end up drawing because it's so much easier. So how you interpret this structural formula is that each point, so here, here, and here are carbon atoms, same thing up here. So the end of a line and the point, like the peak, I guess that you would call it, is a carbon atom. And then if there's nothing else actually written there, then you assume that hydrogens are used to fill the rest of the bonds. How you would draw something with a double bond, you would do it like that. And I know it's really sloppy, but nah, that would be a double bond. So basically you're saying there's a C, double bond to a C, single bond to a C. Okay, so this one is here. This carbon is this one, and this carbon is here. And because there's nothing else written, that implies that you just fill in the rest of the 4 possible bonds with hydrogen. So the first carbon already has 2 bonds, 1, 2 from the double bond. So then I would put 2 hydrogens on the edge. So the first carbon now has 4 full bonds. The middle carbon has 3, 2 from this double bond and 1 from that one. So there's only 1 carbon to fill. Doesn't matter which side you put it on. And the carbon on the right-hand side in the purple, that only has 1 bond. So we need to fill the last 3 hydrogens. Okay, but like I said, you'll get practice and you'll get used to it. It gets really easy. Okay, so you see on the left, drawing out the expanded structural formula is the same as the condensed version. So for now, this is much preferable, right? Okay, so the last thing is the 2 different types of isomers. Isomers are broken down into either being structural isomers or geometric isomers. A structural isomer is where the atoms are bonded together in different orders, but again, they have to have the same formula. So on the screen in the top, you see 2 structural isomers. So you've got butane, which has 4 carbons, if you count them, 1, 2, 3, 4, and it has 10 hydrogens, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, C4, H10. On the right-hand side, you have a compound called methylpropane, but if you count the carbons, 1, 2, 3, 4, C4, and the hydrogens, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, C4, H10. They have different names because they have different structures, which means they're going to have different physical and chemical properties. Okay, that's a structural isomer. Here is a geometric isomer. Now, the key to a geometric isomer and understanding if a compound can have a geometric isomer is whether or not there are single or triple bonds. And to explain why, I gotta turn my camera back on. So, all right, the reason why organic compounds that have single bonds cannot have geometric isomers is because if you have a single bond, like just pretend my fingers are carbon atoms, the carbon atoms and whatever is attached to the rest of this, right? So if this is like a CH3 group and a CH3 group in my hands, they can rotate freely around. So even if I have something like, let's say my pinky fingers are chlorine attached to the carbon, which is attached to the Q-tip, which is the single bond. And I can twist like that, or I can twist like this. So that's not different, right? Because it's free to move. However, if I have a double bond, so the Q-tips are the only thing I have lying around to demonstrate this. If I have a double bond, I can't twist because I'll end up twisting the bonds, and that can't happen. So a double bond and a triple bond create a rigidity or an inflexibility, which prevents the 2 groups that are attached to either side from twisting. So I just wanted to show you that's the easiest way to describe when you can have geometric isomers. So you can only have geometric isomers if there's double or triple bonds present. And then it depends on which kinds of functional groups are attached to either side of that bond. So it only pertains to functional groups which are on either side of that bond. If you have a functional group further down the line, doesn't matter. You're only looking at what's attached to the carbons that are participating in the double bond. So the way that it works is because this is rigid and you can't twist it, you either have a cis isomer, and cis means it's on the same side. So these are the functional groups. They are on the same side of the bond. Or you have trans, and that's when they are on opposite sides of the double bond. So the order of the atom bonding is the same, but the arrangement of atoms in space is different, and that's why it's called a geometric isomer. So again, when in this example, chlorine is the functional group that is making the double bond cis or trans. When it's on the same side, it's called cis, opposite sides, trans. Again, if, I don't know why it's not working, that should be animated and twisting around, but if this, these are carbon atoms, these two can twist around. And so even if this is chlorine, it's still not a geometric isomer because they can freely rotate. Oh, well, okay, it's not quite rotating the way I wanted it to, but because single bonds allow for free rotation, you can only have structural isomers, not geometric. Okay. So looking at this, these two structural formulas, and this is where it gets a little bit tricky. You have to make sure that if you draw something differently, it's not just a flipped or mirror image of something that you think might be an isomer. So these structures look different, but they're actually the same, because if you take this one and you flip it vertically, like upside down, it becomes this. It's the same thing. The whole molecule, just flip it. Same thing. In both, the two hydrogen atoms are on one side, and on the other side, you have one hydrogen and one chlorine. So they are not geometric isomers. So a molecule can have a geometric isomer only if two carbon atoms in a rigid structure each have two different groups attached. Okay, so two reasons why these are not geometric isomers. One is that they're just mirror images. Sorry if you can hear that, that's my dog dreaming. And number two is that there's only one non-hydrogen attached. You need to have two. Again, geometric isomers are important to distinguish because they have different physical and chemical properties. Some of them are even known to differ in physiological or biological behavior as well. If you've ever seen like Discovery or Animal Planet shows and you understand how pheromones work, and like, I mean, we've all seen trails of ants, right? So ants know where to go because the scouts that originally go out to find food, when they do find a source of food, they go back to the nest. And as they do, they release pheromones that tell the worker ants, they leave a trail to follow. And it's the same thing with bees, when like how they know who the queen is, because the queen starts releasing a pheromone called the queen factor. It's literally called the queen factor. And different pheromones are going to communicate with the insects in different ways. For example, like I said, for ants, there's a pheromone to tell the worker ants this is where food is. There's other pheromones that are released when an ant dies. And so then I don't know what kind of ant goes to take them away, probably another worker, but they take the ant away from the nest in case it's like infected with something. It's just different ways of communicating. Okay, another example of geometric isomers. Natural unsaturated fatty acids are mainly cis fatty acids. This is actually useful in your real life. Hydrogenation, which is a process of converting vegetable oil into solid fats. So vegetable oil is an unsaturated natural fatty acid, and we hydrogenate it, which means that we break the double bonds by adding hydrogen. That's why it's hydrogenation. And it turns it into solid fat, so we can have margarine. I think you guys like margarine, something like that. In English, we say margarine. And so during the process of hydrogenation, we turn these cis fatty acids into trans fatty acids. And there are health risks associated with trans fat. I would be interested to read any current studies that are done on trans fat, because I know a lot of these things tend to change with time. Okay,